In the summer of 1977, while the world was watching Star Wars and our first Apple computers, two small machines left Earth on a journey that was supposed to last 5 years. They are still going. They have never stopped. The summer of 1977 was loud and full of itself. Star Wars had opened in May and was still selling out cinemas across the United States. The Bee Gees were on every radio. Elvis Presley died on August 16th, and the news moved through the country like a slow, stunned current. The Apple II had gone on sale in June, the first mass-produced personal computer, and the people who bought one mostly had no clear idea yet what they would do with it. It was the kind of summer that felt, from inside it, like the center of something. On the morning of August 20th, none of that was on the minds of the team at Launch Complex 41 at Cape Canaveral, Florida. They were focused on a spacecraft sitting at the top of a Titan I Centaur rocket, a machine about the size of a small car, weighing 722 kilograms, carrying 11 scientific instruments and a golden record waiting. If you have found this video and you are settling in for the night, this is where you are meant to be. Subscribe to Simple Science and stay with us. Every story we tell is designed to carry you quietly through the dark. At 10:29 in the morning, Eastern Time, the rocket lifted off. The spacecraft it carried was designated Voyager 2, though it launched before its twin. Its trajectory was slower and more deliberate, designed to carry it past not just Jupiter and Saturn, but potentially beyond, to the outer planets that no spacecraft had yet visited. 16 days later, on September 5th, its companion, Voyager 1, launched on a faster path from the same facility. Within months, Voyager 1 would overtake Voyager 2 in distance from Earth, and the numbering that seemed backward would remain, a small permanent quirk in the mission's official record. Both spacecraft were built at the Jet Propulsion Laboratory in Pasadena, California, a facility run by NASA and managed by the California Institute of Technology. JPL had been designing deep space since the late 1950s, and the Voyager program was the most ambitious they had attempted. The total budget for the mission was set at $865 million. In exchange, NASA expected 5 years of science data from Jupiter and Saturn, 2 planets, perhaps some moons, and then silence as the spacecraft moved beyond the range of their instruments' usefulness. What actually happened was something else entirely. The mission had been designed around a rare opportunity. The 4 outer planets of the solar system, Jupiter, Saturn, Uranus, and Neptune, were moving into a configuration that would occur only once every 176 years. In this configuration, a spacecraft launched from Earth with the right trajectory could visit all 4 planets in sequence, using each planet's gravity to accelerate itself toward the next, without carrying the enormous fuel reserves that a direct mission to Neptune would have required. The window to exploit this alignment opened in 1977 and would close by the early 1980s. The next opportunity would come in the 2150s. This was the reason for 1977, not politics, not budget cycles, not any particular readiness of technology. The planets had arranged themselves into a formation that lasted roughly a decade, and NASA had spent that decade preparing for the launch window, miss it, and the next human who would have the same opportunity would live in a world as far from 1977 as 1977 was from the early 1800s. The people who built and launched the Voyagers knew this. They had spent years calculating trajectories, testing instruments, negotiating budgets, and building 2 spacecraft that were meant to survive 5 years in the vacuum of space. 5 years was the design life. It was the engineering guarantee. It was, in the official framing of the mission, as far into the future as anyone was being paid to think. On August 20th, with the summer of 1977 still burning around them, they pressed ahead. The rocket climbed. The spacecraft separated from the upper stage. The solar system opened up ahead of it, enormous and mostly dark, with 4 gas giants waiting at varying distances like markers on a course no human had ever run. Somewhere in Florida, people were listening to the Bee Gees. Somewhere in California, engineers at JPL were watching the tracking data and beginning to breathe. The 5-year mission had started. No one involved fully believed it would stop there. The most relaxing facts about the Voyager spacecraft to fall asleep to Chapter 2. A window that opens once every 176 years. In the summer of 1964, a young engineer at JPL named Gary Flandreau was given a straightforward assignment: study possible trajectories for missions to the outer planets. It was background work, the kind of task that fills notebooks and rarely changes anything. Flandreau sat down with orbital calculations and started running the numbers on where Jupiter, Saturn, Uranus, and Neptune would be positioned over the coming decades. What he found stopped him. In the late 1970s, the 4 outer planets were going to align on one side of the Sun in a configuration that would allow a single spacecraft to visit all of them in sequence, not by burning through enormous quantities of fuel to power from one planet to the next, but by using each planet's gravity as a slingshot, stealing a tiny fraction of the planet's own orbital momentum and flinging the spacecraft onward faster toward the next destination. The mathematics showed that this approach would reduce a trip to Neptune from more than 30 years to roughly 12. The total window for launching a mission that could exploit the alignment fully would last only a few years, in the late 1970s. After that, it would close. The next opportunity would come in the 2150s. Flandreau brought his findings to JPL leadership in 1965. The concept became known as the Grand Tour, and for a period in the late 1960s, NASA planned an ambitious version of it. 4 spacecraft, 2 trajectories, visiting every outer planet, including Pluto. The budget required was substantial, and in the early 1970s, as NASA's funding tightened after Apollo, the Grand Tour was scaled back. The 4 spacecraft became 2. The objectives narrowed to Jupiter and Saturn, with the possibility of extending further only if the spacecraft survived, and the science justified it. The mission that had once promised a comprehensive survey of the outer solar system was now officially a 5-year program to study 2 planets. Unofficially, everyone who understood the alignment knew what was really at stake. The gravity assist technique that made the Grand Tour possible had been worked out mathematically by Michael Minovich, a UCLA graduate student, in the early 1960s. Minovich showed that a spacecraft falling into a planet's gravitational field along the right approach path would exit that field moving faster than it entered. The difference in speed coming from the planet's own orbital velocity. No fuel burned, no engine firing, just geometry and gravity. The Soviet Union had demonstrated the principle as early as 1959, when the Luna 3 probe used the Moon's gravity to arc around and photograph the far side for the first time. But Minovich provided the mathematical framework that made multi-planet tours calculable, and Flandreau applied it to the outer solar system opportunity sitting on the horizon. The physics of how this works is worth sitting with for a moment. Imagine a planet moving through space along its orbit. A spacecraft approaches from behind, falls into the planet's gravitational field, curves around it, and flies out the other side. From the planet's perspective, the spacecraft came in at a certain speed and left at the same speed. From the perspective of the Sun, however, the spacecraft has added the planet's own orbital velocity to its path. It exits the encounter faster than it arrived. The planet, which has a mass billions of times greater than the spacecraft, loses an immeasurably tiny fraction of its orbital energy. The spacecraft gains it all. For Voyager 2, this process played out 4 times. Jupiter's gravity accelerated the spacecraft and redirected it towards Saturn. Saturn's gravity bent its path toward Uranus. Uranus sent it toward Neptune. Each encounter added speed and changed direction, threading the spacecraft through the solar system along a course that had been calculated years in advance, to within tolerances measured in minutes and kilometers, across journeys of hundreds of millions of kilometers. The margin for error at each flyby was extraordinarily small. Arriving too early or too late, too close or too far, would have broken the chain. The people who planned these trajectories worked with the computing resources of the mid-1960s and early 1970s. There were no personal computers. Calculations were done by hand and checked by mainframe. The confidence they placed in these numbers. Enough to build 2 spacecraft and commit them to a 12-year journey on the strength of the math, was of a particular and striking kind. The alignment did not wait for anyone to be ready. It moved on its 176-year cycle regardless of human timelines, funding decisions, or engineering setbacks. The planets were going to be in that configuration in the late 1970s, whether or not anyone launched a spacecraft to take advantage of it. The fact that 2 spacecraft did launch on time in 1977, and that both survived long enough to complete not just the Jupiter-Saturn mission, but the full Grand Tour, is the result of a very specific kind of preparation. The kind that begins 13 years before it is needed, with a young engineer running orbital calculations in a notebook and understanding, before anyone else did, exactly what was coming. Each Voyager spacecraft has a launch mass of 721.9 kilograms. For comparison, that is roughly the weight of a small family car stripped of its engine and interior. It is not a large machine. Standing beside the full-scale development test model on display at the National Air and Space Museum in Washington, most people's first reaction is surprise at how compact it is. The structure at the core of each spacecraft is a 10-sided aluminium frame, 47 centimeters high and 1.78 meters across. This central bus holds the computers, the communications equipment, and the power distribution systems. Everything else extends outward from it on booms, each one positioned to keep instruments away from the spacecraft's own heat sources and the interference generated by its own electrical systems. The most prominent feature is the high-gain antenna, a parabolic dish 3.66 meters in diameter, mounted on top of the central bus and pointed constantly at Earth. Every instruction the spacecraft receives and every piece of data it transmits travels through this dish. It is the Voyager's ear and its voice simultaneously, and keeping it aligned with Earth requires a precise 3-axis stabilization system that uses both gyroscopes and star trackers. The spacecraft locks onto the Sun for one reference point and on the bright star Canopus for another, using these two fixed lights to establish its orientation in space at all times. On one side of the central bus, a science boom extends outward roughly 2.5 meters, terminating in a steerable scan platform that carries the cameras, the ultraviolet spectrometer, the infrared spectrometer, and the photopolarimeter. This platform can be pointed independently of the spacecraft body, allowing scientists to track a moon or a ring system as the spacecraft flies past it, holding the target in frame for minutes at a time, even as the vehicle moves at tens of thousands of kilometers per hour. On the opposite side, a magnetometer boom extends 13 meters outward. Magnetic field measurements require the sensor to be placed as far as possible from the spacecraft's own metallic structure, which generates its own weak field that would contaminate the readings at shorter distances. 13 meters is the distance the engineers calculated was necessary to get clean data. Below and away from the science instruments, a third deployable boom holds 3 radioisotope thermoelectric generators. These are the power source, and their position on a boom serves a dual purpose. It keeps their radiation away from the sensitive instruments on the science boom, and it keeps the spacecraft body itself at a manageable temperature. The RTGs run warm. Placing them at a distance manages that warmth deliberately. 2 whip antennas, each 10 meters long and oriented perpendicular to each other, extend from the spacecraft for the plasma wave and planetary radio astronomy instruments. From directly above, a fully deployed Voyager looks something like a satellite dish with an assortment of booms radiating outward in different directions, each one carrying a specific purpose, each one positioned to avoid interfering with the others. Attached to the side of the central bus, not on any boom but fastened directly to the spacecraft body, is the golden record, a 30-centimeter gold-plated copper disc in an aluminium protective sleeve. Its mass is negligible in the context of the spacecraft's total weight. Its presence contributes nothing to the mission's scientific objectives. It is there because the people who built these spacecraft understood they were building something that might outlast every institution that created it, and they wanted to say so. The 11 scientific instruments carried by each spacecraft were selected from hundreds of proposed experiments. They cover the electromagnetic spectrum from ultraviolet to radio wavelengths, measure charged particles, and magnetic fields, analyze the composition and temperature of atmospheric gases, and detect cosmic rays. The total weight of all instruments combined is approximately 105 kilograms, about 14% of the spacecraft's total mass. Each Voyager was designed to last 5 years in the harsh radiation environment of deep space. The redundant systems, the careful shielding, the conservative power budgets, everything in the design was aimed at ensuring 5 years of reliable operation. The engineers who built these machines were precise, methodical people who believed in working within verified margins rather than pushing assumptions. They built better than they knew. The machines they designed for 5 years are still working, still transmitting, still carrying their golden records, 48 years after the day they left the ground. The phrase gravity assist makes the technique sound more deliberate than it actually is. The planet does not help. The planet does not care. What happens is purely mechanical, a consequence of orbital physics that was working long before anyone calculated it, and will keep working long after the last spacecraft has gone silent. When a spacecraft approaches a planet, it falls into the planet's gravitational field and accelerates. As it swings around the planet and escapes on the other side, it decelerates by the same amount relative to the planet. In the planet's reference frame, the spacecraft enters and exits at the same speed. Energy appears to be conserved. Nothing unusual seems to have happened. But the planet is not stationary. It is moving through space, along its orbit, around the Sun, carrying its gravitational field with it. When the spacecraft swings through that moving field, it borrows from the planet's orbital velocity. From the Sun's reference frame, the spacecraft exits the encounter moving faster than it entered. The planet, whose mass is billions of times greater, loses an immeasurably tiny fraction of its orbital energy. The spacecraft gains all of it. This is not a trick. It is not an exploit of some loophole in physics. It is a direct energy transfer, conserved exactly in the full accounting that includes the Sun, the planet, and the spacecraft together. The planet slows down by an amount too small to detect. The spacecraft accelerates by an amount that can mean the difference between reaching Neptune in 12 years or never reaching it at all. The mathematical framework for calculating this transfer was worked out in the early 1960s by Michael Minovich, a graduate student at UCLA who was working on a summer project at JPL. Minovich recognized that previous treatments of gravitational encounters had framed them from the planet's reference frame and missed the energy gain that was visible only from the Sun's reference frame. His calculations showed that a spacecraft could, in principle, use a sequence of planetary flybys to travel anywhere in the solar system with far less propellant than a direct mission would require. In 1964, a JPL engineer named Gary Flandreau applied Minovich's insight to the specific geometry of the outer solar system and discovered that the alignment of Jupiter, Saturn, Uranus, and Neptune due in the late 1970s would allow a single spacecraft to visit all 4 planets in sequence. Each planet's gravity would bend the spacecraft's trajectory and increase its speed, threading it toward the next destination, like a ball passing between magnets. Flandreau calculated that without gravity assists, a mission to Neptune from Earth would take more than 30 years. With them using the 1977 alignment, it would take 12. For Voyager 2, the chain played out exactly as calculated. Jupiter's enormous gravitational field bent the spacecraft's trajectory and added enough velocity to redirect it toward Saturn. Saturn's gravity pulled it in, accelerated it, and released it on a new heading toward Uranus. Uranus redirected it toward Neptune. Each flyby was planned years in advance, with the spacecraft required to arrive at a precise point in each planet's gravitational field, within a margin measured in minutes after a journey of hundreds of millions of kilometers. The precision required was extraordinary. At Jupiter, arriving even slightly off the planned approach path would have produced a different exit vector, sending the spacecraft on a trajectory that would not intercept Saturn correctly. Every calculation downstream of Jupiter depended on the accuracy of the Jupiter flyby. Every calculation downstream of Saturn depended on the Saturn flyby. The entire chain had to work in sequence without the ability to make significant course corrections at each stage. It worked every time. There is something deeply calming in this, once you sit with it. The Voyagers were not guided by any force that knew where they were going. They simply fell and were caught and fell again, from one gravity well to the next, across a solar system that was itself moving through space. The calculations said it would work. The universe obliged. Astronomers had been looking at Jupiter through telescopes for nearly 4 centuries before Voyager 1 arrived. Galileo had seen its 4 largest moons in 1610. The Great Red Spot had been observed continuously since the late 1600s. By 1979, Jupiter was one of the most studied objects in the night sky, and the scientists waiting for Voyager's data thought they had a reasonable understanding of what the spacecraft would find. They were wrong about almost everything that mattered. Voyager 1 made its closest approach to Jupiter on March 5, 1979, passing within 277,400 kilometers of the planet's cloud tops. Photography had begun in January of that year, when the spacecraft was still far enough away that its images already exceeded the best ever taken from Earth. Over the course of the encounter, Voyager 1 took almost 19,000 photographs. Voyager 2 followed 4 months later and took more than 33,000 images during its own approach and departure. The Great Red Spot, which telescopes had revealed as a roughly oval feature of uncertain nature, turned out to be a complex storm rotating counterclockwise, embedded within a banded cloud system far more turbulent and structured than anyone had anticipated. The cloud bands, visible from Earth, dissolved at Voyager resolution into intricate patterns of swirling eddies and smaller storms. The atmosphere of Jupiter was not the relatively simple, banded structure that ground-based observations had suggested. It was in constant motion, layered, complex, and driven by internal heat as much as by solar radiation. But the discovery that stopped people in their tracks had nothing to do with Jupiter itself. 4 days after the closest approach to the planet, Linda Morabito, an imaging scientist at JPL, was processing a Voyager 1 image of Io taken the previous day. Her task was to identify background stars for navigation purposes She applied a brightness stretch to the image to bring out faint stellar targets. Something else came with it. A gigantic umbrella-shaped plume rising from the limb of the moon, extending more than 300 kilometers above the surface. Io had a volcano erupting. It was the first active volcanism ever seen on any body in the solar system other than Earth. Before Voyager, Io had been expected to look much like the moon. Geologically dead, crater-covered, billions of years of impacts frozen in its surface. Instead, Voyager 1 ultimately identified 9 actively erupting volcanoes. The volcanic plumes ejected material at velocities up to 1.05 kilometers per second, approximately 20 times faster than the ejection velocity of Mount Etna. The surface of Io was being continuously resurfaced by lava and volcanic deposits, which explained what had confused some earlier analysts. The complete absence of impact craters. The surface was too young and too active to preserve them. The energy source turned out to be tidal heating. Io orbits very close to Jupiter, and the gravitational pulls of Jupiter and the 2 other large nearby moons, Europa and Ganymede, flex Io's interior constantly, generating heat the way a repeatedly bent wire generates heat. The interior of Io is in permanent frictional turmoil, and the volcanism is its release valve. This discovery, made incidentally by a navigation engineer looking for star positions, became one of the most significant planetary science findings of the 20th century. It was the first evidence that geological activity was not unique to Earth, and the first indication that tidal heating could sustain geological processes on bodies far from the Sun. The implications for other tidally heated moons, Europa's possible subsurface ocean prominently among them, followed directly from what Morabito found that morning in her image processing workflow. Voyager also discovered a thin ring around Jupiter, previously unknown, and confirmed 2 new small moons. The ring discovery transformed understanding of the outer solar system, Jupiter, Saturn, and eventually all 4 giant planets turned out to have ring systems, each one unique, each one invisible or ambiguous from Earth. Everything scientists thought they knew about the outer solar system before Voyager arrived at Jupiter needed revision, not because what they knew was careless or wrong in method, but because the resolution available from Earth was simply not sufficient to show what was actually there. Voyager closed that distance. What it found was more active, more violent, more strange, and considerably more alive than anyone had expected a system 5 times further from the Sun than Earth to be. Before Voyager, Saturn's rings were one of the most familiar features of the solar system. Every astronomy textbook showed them. 3 or 4 broad, distinct bands separated by a handful of clear gaps, stretching out flat and symmetrical around the planet's equator, the Cassini division. The dark gap between the 2 main rings had been known since 1675. The rings appeared, from Earth, to be a fixed and relatively simple structure. Voyager 1 arrived at Saturn on November 12, 1980, and within hours of the first high-resolution images arriving at JPL, that familiar picture was gone. The rings were not 3 or 4 bands, they were thousands. At Voyager resolution, the ring system resolved into an almost uncountable number of individual ringlets, some dense and bright, some thin and diffuse, separated by gaps of varying sizes. The Cassini division, which from Earth appeared empty, contained ringlets of its own. The ring system was not a handful of discrete structures. It was more like the grooves in a vinyl record, continuous, closely spaced, varying in their properties, but extending without clear breaks across the full width of the system. This was the first surprise. The second was the F-ring. The F-ring is a narrow structure at the outer edge of the main ring system, discovered by the Pioneer 11 spacecraft during its Saturn flyby in 1979. Voyager revealed it to be not a single ring, but a multi-strand structure, with a distinctly braided appearance, the strands winding around each other in a configuration that should not be dynamically stable. Two small moons, later named Prometheus and Pandora, orbit on either side of the F-ring and act as shepherd moons, their gravitational influence confining the ring material into its narrow track. The braiding and the shepherd moons were both discoveries Voyager made in 1980, and neither had been predicted. The spokes were stranger still. In the B ring, the broadest and brightest of Saturn's rings, Voyager's cameras caught radial streaks, dark markings that extended outward from the planet like the spokes of a wheel, appearing and disappearing over the course of hours. Ring particles orbit Saturn at different speeds depending on their distance from the planet, so any radial feature should be sheared apart quickly by the differential orbital velocity. The spokes persisted. They co-rotated with the planet's magnetic field rather than with the ring's orbital motion, which implied that electromagnetic forces were playing a role in their formation, a phenomenon that had no precedent in ring physics. The rings are composed primarily of water ice particles, ranging in size from grains smaller than a sand grain to house-sized boulders. The size distribution within any given ringlet varies. The optical depth, a measure of how much light passes through, varies from ring to ring and from point to point within rings. No two ringlets are identical. The system has a complexity that is still not fully understood, despite the additional 13 years of study carried out by the Cassini spacecraft, which orbited Saturn from 2004 to 2017. After its Saturn encounter, Voyager 1's trajectory carried it out of the plane of the solar system permanently. The flyby had been deliberately designed to pass close to Titan, Saturn's largest moon, which was known to have an atmosphere and was of specific scientific interest. That close Titan pass required an approach geometry that, after Saturn's gravity had finished with it, sent Voyager 1 upward and outward, away from the plane where the remaining planets orbit, ending its planetary career but beginning a longer journey toward interstellar space. Voyager 2 reached Saturn in August 1981, nearly a year after Voyager 1, and photographed the ring system in detail that even the first flyby had not achieved. Its approach geometry had been kept compatible with continuing onward to Uranus and Neptune. When the Saturn encounter concluded successfully and the spacecraft remained healthy, NASA made the decision to extend the mission. The grand tour that had been funded only as far as Saturn was going to continue. Less than 9 months before Voyager 1's launch date, NASA approached Carl Sagan with a request. The agency wanted a message attached to the spacecraft, something that could represent Earth to any intelligence that might someday encounter the probe in interstellar space. Sagan had done something similar before. He had designed the Pioneer plaques, simple gold anodized aluminium panels etched with diagrams of a man, a woman, the spacecraft's origin point in the solar system, and a few key scientific references. For Voyager, he wanted to go further. The result was the Golden Record, a 30-centimeter gold-plated copper disc intended to last 1 billion years in the vacuum of space, carrying sounds and images selected to represent the diversity of life and culture on Earth to any reader sophisticated enough to decode it. The contents were selected by a committee chaired by Sagan at Cornell University, working under intense time pressure. The selection of material took almost a year, running in parallel with the spacecraft's final assembly and testing. Every choice was a deliberate argument for what mattered most. The record contains 116 images, encoded in analog form as a series of scan lines, with instructions on the record's cover for how to decode them. The images range from scientific diagrams of mathematics, physics, and the solar system's structure to photographs of landscapes, animals, plants, human beings at various stages of life, and human-made objects. There are photographs by Ansel Adams. There is a diagram of DNA. The audio begins with greetings in 55 languages, from Akkadian, an extinct language of ancient Mesopotamia, to Wu, a dialect of Chinese. One of the greetings, in the Amoy dialect, says simply, "Friends of space, how are you all? Have you eaten yet?" The selection of 55 languages was made to cover the languages spoken by the vast majority of living people on Earth, while also including languages of historical importance. There is also a 12-minute montage of sounds from Earth: wind, rain, thunder, surf, the songs of birds and whales, a human heartbeat, laughter, footsteps, the sound of a locomotive, a tractor, a kiss, the ordinary sounds of a living planet assembled into a document of what it was like to be alive here. 90 minutes of music follows. The selection ranges across cultures and centuries. Bach's Brandenburg Concerto No. 2 in F major, performed by the Munich Bach Orchestra. Johnny B. Good by Chuck Berry. A Pygmy Girl's Initiation Song from the Democratic Republic of Congo. Azerbaijani bagpipes, Australian Aboriginal songs, Georgian choral music, a Navajo night chant, Beethoven's String Quartet No. 13, 28 tracks in total, drawn from every inhabited continent, and spanning centuries of human musical practice. One track on the record is unlike any other. Anne Druyan, who served as creative director of the Golden Record project and later married on Carl Sagan, recorded an hour-long electroencephalogram, her own brainwave activity captured while she meditated on the history of Earth and the nature of human experience. The hour was compressed into a single minute to fit on the record, whatever that signal means. If anything, to a civilization billions of years from now that finds it, it is the most intimate thing the record carries. A minute of one human mind thinking. The record was designed to be played at 16 wine revolutions per minute. The cover includes a diagram showing a pulsar map indicating Earth's location relative to 14 known pulsars, a stylus, and instructions for playing the disc, all encoded symbolically so as to be interpretable without prior knowledge of human conventions. Sagan estimated the odds of the record ever being found and played by an extraterrestrial civilization as very small. He said that openly. But he also said that launching it said something worth saying about the species that built it. That we were here. That we listened to Bach and Chuck Berry and the songs of whales. That we considered the vast silence around us and responded with music. Each Voyager carries one. Right now, both records are moving away from Earth in opposite directions at roughly 17 kilometers per second, carrying the Brandenburg Concerto into the dark space between the stars. When Voyager 1 left Saturn in November 1980, its planetary career was over. The close Titan flyby that had made its Saturn encounter so scientifically valuable had also sent it onto a trajectory that took it up and out of the orbital plane of the planets. There were no more planets in its path. It was heading into deep space, and it would never fly past another world. Voyager 2 had a different arrangement. Its trajectory through the Jupiter and Saturn flybys had been kept compatible with continuing onward. And when Saturn was successfully completed in August 1981, NASA authorized the extension. Voyager 2 would continue to Uranus and Neptune, becoming the first spacecraft to visit either planet and remaining, to this day, the only one. The Uranus encounter came on January 24th, 1986. By that point, Voyager 2 had been traveling for 8.5 years, and its instruments had spent years in the cold radiation environment of deep space. The primary radio receiver had failed years earlier. The backup receiver worked, but only partially. The engineering team had adapted, developing workarounds that allowed the mission to continue despite the hardware degradation. That adaptability would be tested throughout the Uranus approach. What Voyager 2 found at Uranus overturned multiple assumptions simultaneously. Uranus had been known to be a tilted planet. Its rotational axis is inclined at roughly 98 degrees from vertical, meaning it orbits the Sun essentially on its side. What nobody had anticipated was the degree to which its magnetic field was offset from both its rotational axis and its geometric center. The field is tilted nearly 60 degrees from the rotation axis and displaced far from the planet's center, producing a magnetosphere that twists and shifts in unusual ways as the planet rotates. No other planet in the solar system has a magnetic geometry like it. Voyager 2 discovered 10 previously unknown moons, bringing the known total at the time to 15, and confirmed faint rings that had been tentatively detected from Earth in 1977. Miranda, one of Uranus's moons, showed a surface that looked like it had been shattered and randomly reassembled. Giant canyons, steep cliffs reaching up to 20 kilometers in height, and geological terrain from multiple different eras mixed together. It remains one of the stranger surfaces observed in the solar system. Neptune was 3 more years away. Voyager 2 arrived on August 25, 1989, flying approximately 4,800 kilometers above the planet's cloud tops, the closest approach of any of its 4 planetary flybys. Neptune had been the least understood of the 4 gas giants, visited by no previous spacecraft, visible from Earth only as a faint blue-green disk. What the flyby revealed was a planet far more dynamic than expected. A massive dark storm system in the southern hemisphere, immediately dubbed the Great Dark Spot by scientists at JPL, was comparable in scale to Earth's entire diameter. Wind speeds measured around Neptune reached 2,100 kilometers per hour, the fastest recorded anywhere in the solar system. The planet emitted nearly 2.6 times as much heat as it received from the Sun, indicating a substantial internal heat source. Neptune was not a passive, frozen world. It was turbulent and internally active. But Triton was the revelation that scientists would talk about longest. Neptune's largest moon, at surface temperatures around -235 degrees Celsius, was the coldest natural body that Voyager had yet observed. Scientists had expected it to be a geologically dead ball of ice. Instead, Voyager 2's cameras detected active geysers, plumes of nitrogen gas erupting from Triton's polar ice cap up to 8 kilometers into its thin atmosphere, leaving dark streaks across the surface where the ejected material settled back down. Active cryovolcanism on the coldest observed body in the solar system, 4.5 billion kilometers from the Sun. Triton's retrograde orbit, moving in the opposite direction to Neptune's rotation, indicated it was almost certainly a captured Kuiper Belt object, gravitationally seized by Neptune at some point in the deep past. Its current orbit is slowly decaying. In roughly 3.6 billion years, it will pass inside Neptune's Roche limit and be torn apart by tidal forces, forming a new ring system. August 25, 1989, marked the end of the Voyager planetary mission. The grand tour was complete. No spacecraft has visited Uranus or Neptune since, and no confirmed mission to either planet exists in the near-term schedule. The full picture of both worlds remains, in several significant respects, what Voyager 2 assembled during its brief passage through each system across a period of hours. Carl Sagan had been asking for the photograph since 1981. By the time the answer finally came, he had made the request 6 times over nearly a decade. The idea was straightforward. Turn Voyager 1's cameras back toward the inner solar system and photograph the planets it had left behind, including Earth, from a distance no spacecraft had ever achieved. Sagan believed the image would be important, not for scientific reasons, but for human ones. At sufficient distance, Earth would be reduced to a point of light, indistinguishable in size from the faint smudge of any other distant object. Seeing that image, Sagan argued, would tell people something about where they actually lived, that no telescope image from Earth's surface could convey. JPL and NASA resisted. The cameras were not designed for this kind of looking backward observation. The geometry required pointing the cameras uncomfortably close to the Sun, risking damage to the optics. The engineering resources needed to plan and execute the sequence were limited, and scientifically, the images would show nothing useful. Planets at that range would be smaller than a pixel in each frame. The data would carry no scientific value by any conventional measure. After 6 requests and 8 years, approval came. On February 14, 1990, Voyager 1 turned its cameras inward and took 60 frames covering 6 planets and the Sun. It was the last time the spacecraft's cameras operated. They were switched off 34 minutes after the sequence completed, conserving power for the long journey ahead. The full set of images took until May 1990 to arrive at Earth, downloaded slowly through the Deep Space Network. When the frames were processed at JPL, the results were, as predicted, scientifically underwhelming. None of the planets showed useful detail. Earth appeared as a point of light, less than a single pixel across, 0.12 pixels to be precise, suspended in a bright band of scattered sunlight created by the camera's optics. The image became known as the pale blue dot. It did not immediately register with the public as what it would eventually become. The raw image is faint and, without context, not obviously remarkable. What carried the photograph into wide public consciousness was what Sagan wrote about it. In his 1994 book of the same name, he composed a passage around the image that has since been read aloud at memorial services and graduation ceremonies, and in moments of personal reckoning around the world. He wrote about how everyone who had ever lived, every king and peasant, every creator and destroyer, every saint and sinner, had lived their lives on a mote of dust suspended in a sunbeam. He wrote about how the image underscored the responsibility to be kinder to one another, and how there was no help coming from elsewhere. He wrote about how the vast and dark cosmos offered no indication that help from somewhere else was on its way. The photograph and the words function together. Separately, the image is a faint smudge, and the words are an essay. Together, they produce something that has made people sit quietly for a long time after encountering them. The Solar System Family Portrait, the sequence Voyager 1 captured that day, includes 6 planets: Venus, Earth, Jupiter, Saturn, Uranus, and Neptune. Mercury was lost in the sun's glare. Mars was not visible due to its position in the sunlit band. Pluto was too faint. In Earth's frame, the planet sits inside a streak of scattered light, a band of sunlight caught by the camera's optics, an accidental halo that Sagan later described as making it look as if the planet were held in a sunbeam. After the cameras went dark, Voyager 1 kept moving. It has never slowed. There is nothing in interstellar space to slow it. The image it took that February remains the farthest portrait of Earth ever made, and will remain so for many decades, until some future spacecraft either replicates the feat or travels even further. The dot in the frame is smaller than the period at the end of this sentence. Everything we know, everyone who ever loved or feared or hoped, is on it. There is no sunlight worth collecting at Jupiter. The intensity of solar radiation at Jupiter's distance from the Sun is roughly 27 times weaker than at Earth. By Saturn, it is 90 times weaker. By Neptune, more than 900 times. The Voyager spacecraft were going to travel beyond the reach of any solar panel system that the engineering of the 1970s could have made practical. They needed a different power source, one that would work continuously, without maintenance, in the deep cold and hard radiation of the outer solar system, for as long as the spacecraft survived. The answer was plutonium-238. Each Voyager carries 3 radioisotope thermoelectric generators, hung on a boom away from the main spacecraft body. Each RTG contains 24 pressed spheres of plutonium-238 oxide, approximately 4 and 5 kilograms of fuel per unit. As the plutonium decays, it releases alpha particles, and the energy of those particles is converted into heat. That heat passes through thermoelectric elements, which use the temperature difference between the hot plutonium core and the cold of space to generate electrical current. No moving parts, no combustion, no mechanism that can wear out in any conventional sense. Just the slow, steady disintegration of atoms releasing energy at a rate determined by the half-life of the isotope. The half-life of plutonium-238 is 87.7 years. This means that every 87.7 years, half of the original fuel has decayed, and the power output has halved. At launch in 1977, the 3 RTGs on each spacecraft generated a combined electrical output of approximately 470 watts at 30 volts, enough to power a few household light bulbs. By comparison, a modern laptop computer requires roughly 50 to 80 watts. The Voyagers were never power-rich machines. Every watt was budgeted carefully, and the science instruments were designed to operate within strict power limits. The RTGs decline at a rate of approximately 4 watts per year. After nearly 48 years of operation, the spacecraft are running on roughly 2/3 of their original power. Some of that remaining power must go to heating critical systems. The electronics and hydrazine propellant lines on board need to be kept above certain minimum temperatures to function, and the declining RTG output means that the thermal margins are tightening. Engineers have responded by shutting down instruments and heaters in sequence. Managing the power budget the way someone managing a diminishing supply of firewood manages heat through a long winter. The systems that have been shut down cannot be restarted. Turning off a heater to conserve power means that the component it was warming cools past the point of recovery. Each shutdown is permanent. The spacecraft that carried 11 instruments at launch now carries only a handful of functioning ones. The survivors of a slow culling driven purely by arithmetic. How many watts remain, and what are they worth spending on? The RTGs will not stop abruptly. They will fade gradually, their output declining in proportion to the decay of their fuel. By some point in the late 2020s, the power available may no longer be sufficient to support any science instrument or to maintain reliable communication. The spacecraft will go silent, but they will not stop moving. Nothing in their path will slow them. They will continue outward at roughly 17 kilometers per second, carrying their golden records, their cold RTGs, their silent instruments, into the dark. The design life of the RTGs was 5 years. The engineers who specified them could not have known, could not have designed for the possibility that both spacecraft would still be operating nearly 5 decades later. The RTGs were built to a specification and within a budget. They were not built with the ambition of lasting half a century. They simply have because plutonium-238 decays at its own pace, regardless of the ambitions of those who chose it. There is something fitting about a spacecraft powered by radioactive decay, a source of energy that works by atoms, slowly, inevitably coming apart, releasing in their disintegration the energy that was locked in them since before the solar system formed. The plutonium in the Voyager RTGs was forged in the cores of ancient stars and incorporated into the solar system when it condensed from the dust of those stellar explosions. It has been decaying at its fixed rate for billions of years. For a few decades of that span, it has been generating electricity for two machines from Earth, moving through interstellar space. It will keep decaying long after both spacecraft have gone silent. The atoms do not know the mission is over. For most of the solar system's measurable extent, the Sun defines the environment. Its light diminishes with distance, but never entirely vanishes. Its magnetic field reaches outward, carried by a constant flow of charged particles called the solar wind. The bubble this wind creates, stretching from the Sun past the orbit of Pluto and far beyond, is called the heliosphere. Everything inside it exists within the Sun's direct physical influence. Everything outside does not. The boundary between the two is called the heliopause. Before the Voyagers, no spacecraft had ever reached it. The theoretical distance of the heliopause had been estimated, but the estimates varied widely, and without direct measurement, the actual distance and character of the boundary remained speculative. The Voyager interstellar mission, as the extended mission was renamed after the planetary work was done, had this as its primary long-term objective: to find the heliopause and cross it. Voyager 1 reached it on August 25, 35 years after launch, at a distance of approximately 121 astronomical units from the Sun, roughly 18 billion kilometers. The crossing was not confirmed immediately. The data showed sharp changes in the particle environment, specifically a dramatic drop in the solar wind particles the spacecraft had been measuring for decades, and a corresponding increase in cosmic ray particles from outside the solar system. But scientists had expected the heliopause crossing to be accompanied by a change in the direction of the magnetic field, and that change did not appear in the initial readings. The confirmation came from an unexpected direction. In April 2013, a burst of solar activity that had occurred back in March 2012 finally reached Voyager 1 and set the surrounding plasma vibrating. The frequency of those vibrations allowed scientists to calculate the plasma density. It was approximately 0.08 electrons per cubic centimeter, close to the value expected for the interstellar medium and dramatically higher than the 0.002 electrons per cubic centimeter measured in the outer heliosphere. Working backward from this measurement, and combining it with a smaller oscillation event detected in late 2012, scientists traced the heliopause crossing to August 2012. NASA officially confirmed on September 12, 2013, that Voyager 1 had entered interstellar space. Voyager 2 crossed the heliopause on November 5, 2018, at a distance of approximately 119 astronomical units from the Sun, heading in a different direction through space. Unlike Voyager 1, whose plasma instrument had failed years earlier, Voyager 2 carried a working plasma detector. What's shocking was confirmed almost immediately, and the direct measurements of the plasma transition provided the cleanest dataset ever obtained at the heliopause. The plasma density jumped by a factor of roughly 20 at the boundary, a sharp and clearly defined transition. What the Voyagers found in interstellar space differed from what most models had predicted. The plasma outside the heliopause is denser, cooler, and more structured than the simplified models had assumed. The magnetic field in the interstellar medium near the heliopause appears partially aligned with the field inside the heliosphere, which surprised researchers who expected a sharper directional change. The boundary itself, rather than being a clean, hard edge, appears to allow some leakage in both directions. Solar particles crossing outward and interstellar particles crossing inward in a thin and complex mixing zone. The two spacecraft crossed the heliopause at different points on its surface, heading in different directions, and measured somewhat different properties. The heliosphere is not a symmetric structure. Its shape is pushed and stretched by the pressure of the interstellar medium it moves through, and different locations on its boundary have different characteristics. The Voyagers, by crossing at two different points, are sampling two different parts of what is essentially the outer skin of our solar system. Both spacecraft are now in interstellar space. They are the only direct sources of in situ measurements of the environment beyond the sun's influence. Everything known about what that environment actually feels like, the density of its plasma, the direction of its magnetic field, the flux of cosmic rays unfiltered by the heliosphere, comes from these two machines. The sun is now behind them, in the same direction as Earth. Both are still transmitting. Somewhere in California's Mojave Desert, a dish 70 meters across is pointing at an empty patch of sky. It is not empty, of course. In the direction it is pointing, somewhere along a line of sight, extending more than 25 billion kilometers into space, Voyager 1 is transmitting. The Deep Space Network is the system that makes this communication possible. It consists of 3 complexes positioned roughly 120 degrees of longitude apart around the Earth. One at Goldstone in California's Mojave Desert, one near Madrid in central Spain, and one at Tidbinbilla near Canberra, Australia. The spacing is not arbitrary. As the Earth rotates, any fixed point in deep space moves through the view of each facility in sequence. When Goldstone loses line of sight over the horizon, Madrid picks it up. When Madrid rotates away, Canberra takes over. The 3 facilities together provide essentially continuous coverage of every point in the sky accessible from Earth around the clock every day of the year. Each complex has several antennas of different sizes and capabilities. The largest at each site is a 70-meter dish, a structure the size of a 23-story building laid on its back. These are the antennas used to communicate with the Voyagers. At their operational frequencies, they can detect signals that arrive at power levels of less than a billionth of a watt. To achieve this sensitivity, the receiving amplifiers at the focus of each 70-meter dish are cooled cryogenically to within a few degrees of absolute zero, reducing thermal noise to levels low enough for the electronics to distinguish the incoming signal from the background static of the universe. The signal itself originates from Voyager's 23-watt transmitter, roughly the power output of a refrigerator light bulb. By the time it has spread outward across 25 billion kilometers of space, following the inverse square law that governs how radiation dilutes with distance. The power arriving at the 70-meter dish is approximately a billionth of a watt. The comparisons used by NASA engineers is that it is 20 billion times weaker than the power needed to run a digital watch. The dish collects this wisp of radio energy from across the entire surface of its 70-meter aperture, focuses it on the cryogenically cooled amplifier, and extracts data from it. The data rate is currently around 160 bits per second from Voyager 1. For comparison, a standard internet connection in a home today delivers millions of bits per second. At 160 bits per second, transmitting a single moderately sized photograph would take hours. But Voyager is not sending photographs. It is sending measurements from its remaining science instruments. Plasma wave data, magnetic field readings, charged particle counts. These measurements are compact. 160 bits per second is enough to carry them, as long as everything on both ends of the link continues to function. The 70-meter dish at the Canberra complex, designated Deep Space Station 43, holds a particular distinction. It is the only antenna in the entire deep space network capable of sending commands to Voyager 2. Voyager 2's trajectory, designed to allow a close flyby of Neptune's moon Triton in 1989, carried it over Neptune's north pole and then out of the solar system in a direction that is only visible to antennas at the southern facilities. DSS-43 in Canberra is the sole transmitter powerful enough and correctly positioned to reach it. In 2020, DSS-43 went offline for major upgrades and remained out of service for several months. During that window, Voyager 2 could be heard but not commanded. Engineers could receive the spacecraft's telemetry through the smaller antennas at Canberra, confirming it was still functioning, but they had no ability to send instructions. If a critical fault had occurred during that period, they would have had to wait. In early 2021, the first test command was sent and received successfully. Voyager 2 responded from 18.8 billion kilometers away, confirming that it had received the call and executed the instructions without issue. The Deep Space Network was built and has been continuously expanded to support missions like Voyager. The 70-meter dishes at all 3 sites were upgraded from their original 64-meter diameter specifically to track Voyager 2 during its 1989 Neptune encounter. The Voyagers made the dishes grow, and the dishes kept the Voyagers talking. The conversation continues. At this moment, Voyager 1 is transmitting. It has been transmitting almost continuously since September 5, 1977. The transmitter uses 23 watts of power drawn from the slowly diminishing output of the 3 RTG units on the spacecraft's boom. 23 watts. A typical incandescent light bulb for a bathroom mirror uses more than that. The signal leaves the spacecraft's 3.66 meter high-gain antenna as a tightly focused beam of radio waves in the X-band frequency range, around 8.4 GHz. Because the dish is pointed precisely at Earth, the beam is directional, which is why it can carry usable data across 25 billion kilometers despite its low power output. If the antenna were pointing in any other direction, the signal would never arrive. The spacecraft's attitude control system, locked onto the Sun and the bright star Canopus as reference points, maintains the antenna's Earth-pointing orientation continuously. By the time that 23-watt signal has travelled more than 25 billion kilometres and spread across a sphere of corresponding size, the power arriving at the 70-metre receiving dish at Goldstone or Canberra or Madrid is less than a billionth of a watt. NASA's comparison is instructive. The signal arriving from Voyager 1 is 20 billion times weaker than the power level needed to operate a digital watch. The entire energy received by the dish over its entire history of Voyager contact would not be enough to light a flashlight for a fraction of a second. To extract data from this whisper, the Deep Space Network uses cryogenically cooled amplifiers at the focus of each 70-metre dish. These amplifiers are cooled to temperatures just a few degrees above absolute zero, because at those temperatures, the thermal noise generated by the electronics themselves falls below the level of the incoming signal. At room temperature, the thermal noise would overwhelm everything. Cold makes listening possible. Once amplified and extracted from the noise, the signal is decoded. The current data rate from Voyager 1 is approximately 160 bits per second. This is the raw measurement stream from the spacecraft's remaining operational instruments. The plasma wave science system, the low-energy charged particle instrument, the magnetometer. Each measurement is a number, a magnetic field vector, a particle count, a plasma oscillation frequency, small quantities of data, precisely defined, transmitted slowly across a distance that takes light itself nearly 24 hours to cross. The signal from Voyager 1 that arrives at a dish today was transmitted nearly 24 hours ago, when engineers at JPL send a command to the spacecraft. They will wait approximately 24 hours for it to arrive. If Voyager responds, they will wait another 24 hours for the reply. A simple exchange, question and answer, takes 2 full days. By the time the answer arrives, Voyager 1 will have moved approximately 3 million kilometers further from Earth than it was when the question was sent. This communication delay is not a problem to be solved. It is simply the physics of the situation. Radio waves travel at the speed of light, and the speed of light, while the fastest anything can move through space, is not instantaneous. At the distances Voyager now occupies, this becomes viscerally real. The spacecraft operates in a regime where human reaction time is meaningless. Any command has to be anticipated, planned, uplinked well in advance of the moment it is needed, and trusted to arrive and execute correctly. There is no possibility of real-time adjustment. JPL engineers have operated under these constraints for nearly 5 decades. They have reprogrammed the spacecraft, rerouted power, repointed instruments, and managed faults, all across a communication link that takes a day each way to complete. The people doing this work have, in a very literal sense, learned to think across spans of time that most human activities never require. The signal is still coming. Right now, somewhere in a control room at JPL, someone is watching the data stream from Voyager 1 arrive at 160 bits per second, each bit a measurement taken by instruments that have been operating since a year when Star Wars was in cinemas and the personal computer had just been invented. The data is still good. The instruments are still working. The signal is still coming. The interstellar medium is not empty. Nothing in space is truly empty, but it is extraordinarily thin. And it is old, and it carries the signatures of stellar events that happened millions of years before the solar system formed. Between the stars, space is threaded with plasma, ionized gas left behind by the deaths of massive stars, compressed and heated by shock waves from supernovae, shaped by magnetic fields that extend across distances measured in light years. The average density of the local interstellar medium near the solar system is roughly 0.1 electrons per cubic centimeter. For comparison, the air you are breathing right now contains approximately 10 billion molecules per cubic centimeter. Interstellar space is not a hard vacuum, but it is extraordinarily close to one. The Voyagers are the only instruments that have ever been inside this region and measured it directly. Everything else humanity knows about the interstellar medium comes from observations at a distance, from telescopes analyzing light and radio emissions that have traveled across interstellar space to reach us. Voyager's data is different. It is in situ measurement, taken from within the medium itself. The difference between measuring the ocean from a satellite and putting a probe in the water. What the instruments have found differs in several ways from what theoretical models predicted. The plasma is denser and colder than the simplest models assumed. The magnetic field in the region just outside the heliopause is partially aligned with the field inside, a finding that surprised researchers who had expected a sharper directional change at the boundary. The heliosphere appears to be leaking in both directions. Solar particles cross outward into interstellar space, and interstellar particles penetrate inward in a mixing zone that is thinner and more structured than anticipated. Cosmic ray levels outside the heliopause are substantially higher than inside. The heliosphere acts as a partial shield, reducing the flux of galactic cosmic rays, which are high-energy particles accelerated by distant supernovae and other energetic events across the galaxy. Inside the heliosphere, the solar wind pushes back against this incoming particle flux. Outside, the spacecraft is exposed to the full galactic environment. Voyager's cosmic ray instruments documented this increase as both spacecraft crossed the heliopause, confirming directly one of the heliosphere's important functions. It moderates the radiation environment of the inner solar system, including Earth. The temperature of the plasma just outside the heliopause, measured by Voyager's instruments, was found to be considerably higher than expected, roughly 30,000 to 50,000 Kelvin in the region immediately beyond the boundary. This was a surprise. Theorists had expected cooler plasma at that location. The high temperature likely results from compression effects at the boundary where the solar wind and interstellar medium press against each other. But the precise mechanisms are still being studied. Both Voyagers are now sampling regions that no predictive model fully anticipated. The interstellar medium near the solar system has its own structure, its own gradients, its own history. Voyager 1 is heading in one direction through this medium, Voyager 2 is heading in another, roughly 35 degrees away in sky coordinates. There, measurements are similar in some ways, and different in others, reflecting the fact that the interstellar medium is not uniform on the scales they are exploring. Every day that both spacecraft continue to transmit, the dataset of direct interstellar measurements grows. No other mission is currently capable of making these measurements. The two spacecraft that were funded to study Jupiter and Saturn, designed to last 5 years, are now the only direct sensors humanity has placed in the space between the stars. The science they are doing cannot be replicated by any telescope or any other instrument currently in operation. The data they send back at 160 bits per second is, in its field, irreplaceable. Outside, right now, both spacecraft are moving through the thin, cold plasma of interstellar space. The instruments are measuring. The antennas are transmitting. The data is flowing toward Earth at the speed of light. Every year, each Voyager loses approximately 4 watts of electrical power. This is not a malfunction. It is physics. The plutonium-238 in the RTGs is decaying on its fixed schedule, and less plutonium means less heat, and less heat means less electricity. The process is continuous, predictable, and unstoppable. The engineers at JPL who manage the mission know exactly how much power each spacecraft has right now, and they know how much it will have a year from now, and the year after that. What they have to decide is what to do about it. The spacecraft needs power for 3 categories of function. The science instruments that collect data, the heating systems that keep critical components above their minimum operating temperatures, and the communication systems that transmit data to Earth. Of these, communications are non-negotiable. Without the transmitter and the antenna control systems, there is no mission. Whatever else must be sacrificed. Those systems stay powered. The heating systems are the next priority, but they are also the most insidious drain. In the cold of interstellar space, certain components require continuous warming to remain functional. The hydrazine propellant used by the attitude control thrusters must be kept above its freezing point. Electronic components have minimum operating temperatures below which they behave erratically or fail. Heaters consume power continuously, and turning one off is a permanent decision. Once a component cools below its tolerance, it may never recover, and that capability is gone. The science instruments are what remain after communications and heating are funded. As power has declined, instruments have been shut down in a deliberate sequence, each shutdown chosen to preserve the highest scientific value for the longest possible time. Some shutdowns happened long ago. The camera systems on both spacecraft were turned off after the pale blue dot image in 1990, partly to conserve power, and partly because the cameras were no longer useful in the dark void between stars where there was nothing to photograph at useful distances. The plasma science instrument on Voyager 1 had failed years before, a hardware casualty of the radiation environment. Instrument shutdowns have continued through the decades. The cosmic ray subsystem on Voyager 1 was turned off in 2024 after 47 years of operation. The process of deciding which instrument to shut down next involves weighing the scientific value of each instrument's remaining data against the cost of the power it consumes, and the risk that keeping it powered poses to the overall spacecraft health. These are not easy decisions. The people making them are saying goodbye to science that cannot be recovered, choosing which window into the interstellar medium to close permanently in order to keep the others open a little longer. The mission's power trajectory suggests that both spacecraft will likely fall below the threshold for any science instrument operation sometime in the late 2020s, and below the threshold for reliable communication perhaps shortly after. The exact timing depends on how efficiently power is managed, and whether the spacecraft continue to function without unexpected failures. JPL engineers are aiming to keep both spacecraft alive through their 50th anniversary in 2027. It is achievable, barely, with careful management. What will not change when the power runs out is the motion. The Voyagers will continue moving outward at roughly 17 kilometers per second, regardless of whether any of their systems are functioning. There is nothing in their path to slow them. They will become silent, and they will keep going. The instruments will stop. The transmitters will stop. The heaters will stop. And the spacecraft will cool to the temperature of interstellar space, somewhere around -270 degrees Celsius. But the machines will still be there, still moving, carrying their golden records. The power budget runs down. The journey does not. Each Voyager spacecraft carries 3 onboard computers. Together, across all 3 systems, they hold a combined memory of approximately 69.63 kilobytes. A single photograph taken on a modern smartphone is several megabytes. The entire computational memory of either Voyager spacecraft would not hold a fraction of one such image. This comparison is by now familiar enough to feel abstract, so it is worth being specific about what those computers actually are. The 3 systems are the Computer Command System, the Flight Data System, and the Attitude and Articulation Control System. The Computer Command System manages instructions and memory, holding 4,096 words of 18-bit memory in each of its 2 redundant units. The Flight Data System, which packages science and engineering data for transmission, holds 8,192 words of 16-bit memory per unit. The Attitude and Articulation Control System, responsible for keeping the antenna pointed at Earth and the spacecraft oriented correctly, holds 4,096 words of 18-bit memory per unit. All 3 are programmed in assembly language, written specifically for the custom processors on which they run. The processors execute approximately 8,000 instructions per second. A modern smartphone processor executes more than 14 billion instructions per second. The Voyager computers are running at a rate that is roughly 1.75 million times slower than a current mobile phone. None of this has prevented the mission from continuing for nearly 50 years. The computers were not designed to be fast or capacious. They were designed to be reliable, redundant, and reprogrammable. Every unit exists in duplicate, so a failure in one does not stop the function. Every unit can receive new instructions from Earth. allowing JPL to modify the spacecraft's behavior in response to changed conditions, degraded hardware, or new scientific requirements. This reprogrammability has been used throughout the mission. Routines written in the 1970s have been modified, supplemented, and worked around many times. In 2024, it became critically important. On November 14th, 2023, Voyager 1 stopped making sense. The flight data system, which packages data for transmission, began producing a repeating, unintelligible pattern of ones and zeros. The carrier signal was present. The spacecraft was still transmitting. But the content was unreadable. 5 months of careful diagnosis followed. Engineers sent a poke command, an instruction telling the flight data system to transmit a complete readout of its own memory. When that readout arrived, a deep space network engineer decoded it and identified the problem. Approximately 3% of the flight data system's memory had been corrupted. A single chip, an RCA CD461C CMS static RAM component holding 256 words, had failed. Whether it had been struck by a cosmic ray particle or had simply worn out after 46 years in deep space could not be determined. It did not matter. The chip could not be replaced. The spacecraft was too far away for any physical intervention. The team had to move the code that had been stored on the failed chip to elsewhere in the flight data system's memory. The difficulty was that no single free block was large enough to hold it all. The engineers divided the affected code into sections, identified and deleted routines left over from Voyager's Jupiter flyby in 1979 that the spacecraft no longer needed, and distributed the fragments across available memory wherever space could be found. The code had to be modified so that all its parts, now stored in separate locations, still functioned correctly as a whole. The fix was transmitted to Voyager 1 on April 18th, 2024. Given the signal travel time of approximately 22.5 hours each way, engineers waited nearly 2 days to find out if it had worked. On April 20th, 2024, Voyager 1 began returning usable engineering data for the first time in 5 months. The team at JPL, gathering in a conference room early that morning, received confirmation at 6:40 a.m. They cheered. The instrument that had processed more than 45 years of planetary and interstellar science on a computer with less memory than a single small image file had been remotely repaired from 15 billion miles away. The computers are still running. So is the mission. Neither Voyager is heading toward any particular star. The trajectories they are following were determined by the planetary flybys they completed between 1977 and 1989, and those flybys were designed for their scientific value, not for any destination beyond the solar system. Both spacecraft are simply moving outward in the directions their final gravitational encounters sent them, into the vastness of interstellar space. But in 40,000 years, Voyager 1 will pass within approximately 1.6 light-years of a star. The star is called Gliese 445, currently located in the constellation Camelopardalis. It is a dim red dwarf, much smaller and cooler than the Sun. Today, it is about 17 light-years from Earth, but stars are not stationary. They move through the galaxy, and Gliese 445 is moving in a direction that will bring it considerably closer to the solar system over the next 40 millennia. By the time Voyager 1 reaches the vicinity of its closest approach, the star will be roughly 3.5 light-years from Earth, closer than the distance from Earth to the nearest star today. Voyager 1 will not enter the Gliese 445 system. Its closest approach will be 1.6 light-years from the star, which is still an enormous distance. For comparison, the current nearest star to the Sun, Proxima Centauri, is about 4.2 light-years away. Voyager 1 will pass closer to Gliese 445 than Proxima Centauri is to us today. It will then continue outward, leaving that star behind and moving into deeper galactic space. At the moment of that closest approach, in roughly 40,000 years, every electronic system on the spacecraft will have been silent for tens of thousands of years. The RTGs will have long since exhausted their useful output. The computers will be cold and dark. The antennas will no longer be transmitting. No signal will arrive from the spacecraft. No signal will be sent to it. It will be an inert object, a piece of human engineering moving through space at 17 kilometers per second, maintaining its velocity without any mechanism required, because there is nothing in interstellar space to slow it down. The golden record will still be attached to its side. The gold plating is designed to preserve the record's surface against the thin particle flux of interstellar space. The record itself is copper electroplated with gold, enclosed in an aluminium protective sleeve. Scientists who designed it estimated its longevity in deep space at approximately 1 billion years. In 40,000 years, it will be in essentially the same condition it is today. Before reaching the vicinity of Gliese 445, Voyager 1 will first enter the Oort cloud, the vast theoretical shell of icy objects that marks the outermost gravitational boundary of the solar system. The Oort cloud is estimated to begin at roughly 1,000 to 2,000 astronomical units from the Sun, and extend to perhaps 100,000 astronomical units. At Voyager 1's current speed, it will reach the inner edge of the Oort cloud in approximately 300 years. Traversing the cloud entirely will take an estimated 30,000 years. This means that the solar system is much larger than its planets suggest. The Oort cloud, invisible and unvisited, extends to a distance that Voyager 1 will spend the better part of 30 millennia crossing, still technically within the Sun's gravitational sphere of influence, even as it moves through what is by any other measure deep interstellar space. 40,000 years from now, 40,000 years after the summer of 1977 and the Bee Gees and Star Wars and the anxious engineers at Cape Canaveral who pressed the launch button, a small machine from Earth will pass silently through the distant neighborhood of a red dwarf star. No one will be there to see it. No instrument will record it. Gliese 445 will not notice. But the record on the spacecraft's side will still carry the Brandenburg Concerto and the sound of rain and whale song and human laughter encoded in the grooves of a golden disc built to last longer than most things humanity has ever made. There is a milestone coming. It is not a spectacular event. No explosion, no collision, No dramatic change in the spacecraft's condition. It is simply a number crossing a threshold. But the threshold is one of those that, once you understand what it represents, has a way of staying with you. On approximately November 15, 2026, Voyager 1 will be one full light day from Earth. A light day is the distance that light travels in 24 hours, approximately 25.9 billion kilometers, or just over 16 billion miles. At that distance, a radio signal traveling at the speed of light takes exactly 24 hours to complete the one-way journey. A command sent from the control room at JPL at 8 a.m. on a Monday will arrive at Voyager 1 at 8 a.m. on Tuesday. If the spacecraft responds immediately, the reply will arrive back at Earth at 8 a.m. on Wednesday. One question, one answer, 2 full days. As of early 2026, the one-way signal time from Earth to Voyager 1 is approximately 23 hours and 30 minutes. The spacecraft is crossing roughly 1.5 million kilometers of additional distance every day. The light day threshold will be reached when the signal time extends its final 30 minutes to reach the full 24-hour mark. It has taken nearly 49 years to get here. Voyager 1 launched on September 5, 1977. It will reach one light day from Earth in November 2026. Light covers that same distance in 24 hours. The spacecraft has taken 49 years to cross it. This comparison is not a criticism of the spacecraft's speed. Voyager 1 is traveling at approximately 61,200 kilometers per hour relative to the Sun, or roughly 17 kilometers per second. It is one of the fastest human-made objects ever launched. But the universe is under no obligation to be convenient, and the speed of light, while the fastest anything can go, covers distances in moments that take spacecraft decades to traverse at any velocity achievable with 1970s technology. The light day milestone will be the first of what are sometimes called light milestones. One light day, then eventually one light week, one light month, one light year. Voyager 1 will not reach 1 light year from Earth for approximately 17,500 more years at its current speed. The milestones stretch out across timescales that exceed recorded human history by orders of magnitude. But the November 2026 milestone, the first of them, is reachable within a human lifetime. People who were alive when Voyager launched in 1977 will still be alive when this happens. The same spacecraft, carrying the same computers and the same golden record, will cross a threshold that no human-made object has ever crossed before. The engineers at JPL are planning to still be communicating with Voyager 1 when November 2026 arrives. The power budget is tight, but the transmitter should still be running. The signal should still be arriving at the deep space network dishes. The data at 160 bits per second should still be flowing. Susie Dodd, Voyager's project manager at JPL, described the milestone in practical terms in late 2025. If she sends a good morning to Voyager 1 at 8 a.m. on a Monday, she will receive Voyager's response at 8 a.m. on Wednesday. 2 days for a greeting to make its round trip. It is difficult to hold that image and not feel something about it. The most distant human-made object, still transmitting still receiving commands, still producing science from a distance so great that the fastest thing in the universe needs a full day to reach it. Built in the early 1970s by people with slide rules and mainframe computers. Still going, still going. In April 2026, NASA shut down another instrument aboard Voyager 1. It had been operating for 49 years, since September 1977, through the Jupiter flyby and the Saturn flyby and the long cruise out of the planetary system and the crossing of the heliopause and the years of interstellar measurement. It had been counting particles. The instrument being switched off was one of the last remaining operational science systems on the spacecraft. It was turned off not because it had failed, but because the power it consumed was needed to keep the transmitter and heating systems running a little longer. This is how the Voyager missions end. Not in a single dramatic moment, but in a slow sequence of farewells. Each instrument that has been powered down over the decades, camera systems, plasma science instruments, cosmic ray detectors, ultraviolet spectrometers, represents a capability permanently retired. The science each one was doing cannot be picked up again. When an instrument goes dark on Voyager, that specific measurement from that specific location in interstellar space stops. There is no other asset that can take over. The JPL teams that manage the Voyagers have spent years making these decisions. The calculus is always the same. How much science does this instrument produce? How much power does it consume? And what else could that power keep alive? The answer shifts as the RTG output falls. An instrument that was worth keeping running 5 years ago may no longer be worth it today, because the power it needs could now be the difference between the transmitter staying on or going silent. The Voyager project manager and project scientist at JPL work with a small team that has maintained the mission for nearly half a century. Some of the engineers who currently support the Voyagers were not born when the spacecraft launched. Some of the older ones who built and launched the original systems are no longer alive. The institutional knowledge of the mission is a living archive that has to be actively maintained, transferred, and preserved. Every year that passes makes that archive harder to hold. There have been moments where the institutional memory almost failed. When Voyager 1's flight data system began sending garbled data in November 2023, JPL engineers had to study 47-year-old documentation to understand how the computer worked well enough to diagnose and fix the fault. Some of the engineers brought in to help were retired. Some of the documentation was on paper. The repair required understanding systems that were designed before most of the people working on them today were in school. The last instrument to operate on each Voyager will eventually go quiet. After that, the spacecraft will still transmit for a time, sending engineering data about the health of its remaining systems. Temperatures, power levels, thruster activity. Then, the power will fall below the threshold for the transmitter, and the signal will stop. That final silence will not be a failure. It will be the conclusion of a mission that was designed to last 5 years, and lasted, in total, somewhere around half a century. It will be the end of the science, but not the end of the journey. The spacecraft will continue moving outward, as they have been moving since 1977 at 17 kilometers per second, without any further need for power, without any mechanism required to sustain their velocity. JPL's current goal is to keep both Voyagers transmitting through their 50th anniversary in 2027. The instruments are declining, the power is declining, but the transmitters are still running. And somewhere in the silence between the numbers, there is still something like a conversation happening. A spacecraft 25 billion kilometers away, sending data, and a team of engineers on a small planet still listening. The launch pad at Cape Canaveral is quiet now. Complex 41, where Voyager 2 lifted off on August 20, 1977, has been rebuilt and modernized in the decades since. The summer that surrounded that launch, the BGs, the first Apple computers, the opening weeks of Star Wars, belongs to a world so changed from this one that it requires active reconstruction to imagine. Most of the engineers who pressed the launch button are gone. The mainframe computers that calculated the trajectories have been obsolete for longer than some readers of this have been alive, and the spacecraft are still moving. Right now, at this moment, Voyager 1 is approximately 25 billion kilometers from Earth, traveling at 17 kilometers per second through interstellar space, carrying a golden record, and 3 slowly decaying RTGs and a computer with 69 kilobytes of memory. Its signal, at 23 watts, is traveling toward Earth at the speed of light. It will arrive at a 70-meter dish in Australia, or California, or Spain, approximately 23.5 hours after it was transmitted. Engineers will decode it at 160 bits per second, and read the magnetic field values and plasma wave frequencies from the instruments that are still running. Voyager 2 is doing the same thing in a different direction. Neither spacecraft is heading toward any particular destination. Neither has a mission endpoint in the traditional sense. They will travel through interstellar space for millions of years after their transmitters fall silent, carrying the only physical objects humanity has ever placed in the space between the stars, heading toward encounters with stars whose names most people do not know, following trajectories that no human mind will track. In 40,000 years, Voyager 1 will pass within 1.6 light-years of Gliese 4 and 45. By that time, the golden record will be the only thing still intact and functional aboard. The Brandenburg Concerto will be there, the sound of rain and wind and surf, the greetings in 55 languages, the brainwave recording of a woman named Anne Druyan, who was thinking about the history of Earth, the voice of a speaker of the Amoy dialect asking, across interstellar space, "Friends, how are you all? Have you eaten yet?" Carl Sagan said, "The odds of the record being found were very small." He said it anyway, not because it was likely to be received, but because the act of sending it said something about the species that built these machines. He called it a message in a bottle. "Cast into the cosmic ocean," he said. The launching of it says something very hopeful about life on this planet. What he meant, in part, was this: that a civilization with the ability to build machines that cross interstellar distances, with the knowledge of physics and orbital mechanics and materials, science required to make them last, chose to use that ability not only for measurement and data collection, but to include, alongside the magnetometers and plasma wave instruments, a record of whale song and Bach and human laughter. That the impulse to put music on a spacecraft was taken seriously by the people who built it, funded it, and launched it. That the engineers and the scientists and the bureaucrats and the politicians who made the Voyager program possible all signed off, in the end, on attaching a golden record to the side of each spacecraft, just in case. That impulse has not stopped. It began before Voyager with the Pioneer plaques. It continued with Voyager, and something of it continues in every human activity that looks outward and asks what else is there, and whether anyone else might be listening. The spacecraft are still transmitting. The signal is still coming. In a control room, somewhere at the Jet Propulsion Laboratory in Pasadena, California is still listening, and out in the dark between the stars, two small machines from Earth are still moving forward. They have never stopped